active galactic nuclei fundamentally are galaxies that have a feeding supermassive black hole in their centers. And those feeding supermassive black holes are ejecting charged particles at relativistic speeds in the form of a jet that goes above and below the spin axis of the supermassive black hole. And so my colleagues and I made this cartoon about 20 years ago, unifying all of the different subsets of active galactic nuclei. And the unification is that we have the same object, that is a supermassive black hole in the middle, an accretion disk surrounded by this dusty torus, and then a jet of material squirting out up and down in this image. And the unification is that all active galactic nuclei are have the same central engine. It's just how we observe them that gives us the difference. So radio galaxies, we see the jet more or less edge on. Quasars, we see them at some low angle, and then blazars, we're looking right down the jet. And theoretically, we're seeing to just above the supermassive black hole where the jet is launched, just outside of the event horizon, perhaps. And so the problem with that is that there's a lot of energy there, and it makes blazars really, really difficult to observe. It was really only with the advent of the Hubble Space Telescope, this is one of my images, where we had tremendously high resolution that allowed us to differentiate between this massively bright nuclear region, in this case, even in the Hubble, this is unresolved, and the very faint host galaxy. And in this image, just, there's a clear distinction between the fuzzy host galaxy, which in this case is a giant elliptical galaxy, and the bright nuclear region, but this is a factor of 10 million to 1. And without the Hubble resolution, we would never be able to see this very faint fuzz. So my work is looking at those galaxies, the giant ellipticals, with the intent of determining what the galaxy does to cause the active nucleus in the middle. In astronomy, NASA funds space-based astronomy predominantly, and NSF funds the ground-based astronomy, optical and infrared and radio. ALMA is well, I'm biased, but it's a spectacular observatory. It's an interferometer with 66 12-meter antennas, and here we get an image during construction, so they're not all there. The longest baseline is 16 kilometers. And an interferometer, again, at the 100,000-foot view, means that all of the elements, that is, these 66 antennas, are all working together. And they're observing the same astronomical object at precisely the same time. And when you do this, and you can do it in any wavelength, for all intents and purposes, it becomes difficult the higher energy the wavelength is. So the visible spectrum is probably as high energy photons as you can, the highest energy photons that you can do with an interferometer in an easy way. And in the optical, it's not easy. In the radio, it's a little bit easier. So what do we do? The individual elements of the telescope, of the array, of the interferometer, observe the astronomical object simultaneously. And by doing that, you simulate a telescope that has a diameter that's the baseline between the two elements of the array. Okay? So if I have a 12-inch telescope here and a 12-inch telescope over there, and I'm observing simultaneously, then I am reproducing, in a virtual sense, a telescope that has the diameter of this room. Now, resolution, that is the finest element that you can see on the sky, scales with the diameter of the mirror or the radio dish. And so the bigger the mirror or the dish, the finer the resolution, the smaller the resolution. So the bigger you go, the more detail you can see. And so this is why we do interferometry in the radio. The problem is that photons are coming in from the astronomical source, at all times. And so, yeah, you have two things observing the same astronomical source at the same time, but you're losing some time information because photons arrive over here and photons arrive over here with a time delay. So what do? Well, in the radio, you can make an interferometer as long as you can timestamp the data coming in at a rate of about 1 part in a billion, so every nanosecond. So these telescopes have masers, which are microwave equivalent of a laser, and the maser sets a time, is a clock. the device uses a maser to very accurately measure time as a clock, and it injects a time signal into the data stream that's coming off of each antenna. So the data stream's coming in, and every billionth of a second, a time stamp is injected into the data stream. Okay, this data then gets shunted via optical fiber to a very large computer. It's called a correlator. The correlator for ALMA is the world's fastest supercomputer, and you measure supercomputer fastness by the number of operations it does per second. And so Frontera does 25 tera operations, teraflops, 10 to the 12 operations per second, 25 times 10 to the 12 per second. And so that's the world's fastest supercomputer. Well, the correlator at ALMA does 250 teraflops. It's just that Frontera is a very smart computer, and it can do very complicated mathematical formula. The correlator at ALMA, all it does is add, subtract, multiply, and divide. So it's a dumb supercomputer, but yet it's the fastest one. Why does it need this massive speed? Because, you know, we have these data streams coming in with the timestamps. So let's say I have just two antennas. This antenna has a timestamp up here. This one has a timestamp over here. When the data come into the correlator says, okay, these are the two timestamps. Let's correlate them and rectify them. And so it lines up the timestamps. And now I have, it's as if I'm observing, you know, those photons coming into one telescope that is whatever the baseline of the data from. So that seems easy, right? But the complexity comes from the fact that antenna number one has to be correlated with 65 other antennas simultaneously. Antenna number two has to be correlated with, you know, another 65 antennas. And so you have all of these baselines, and the computational requirements are enormous. So the supercomputer is the fastest on Earth, and because of this, the ALMA Observatory is the most complex scientific instrument ever constructed. It's sitting up here at 16,670 feet above sea level in big plateau, the Chagnon-Tor Plateau in northern Chile, in the middle of the Atacama Desert. And it's in the middle of the Atacama Desert because the wavelength that it observes at, in the millimeter and submillimeter part of the radio spectrum, is heavily absorbed by water vapor in Earth's atmosphere. And so, you know, we've all heard that the Atacama is the world's driest place. 1 millimeter every century or so. Well, so that's why we're there, because the atmospheric water vapor is very low. What you've heard from our experience in the last 10 years at ALMA is probably wrong. Why? Because in February, there's torrential rainstorms, and in the winter, you know, in June in the southern hemisphere, there's many meters of snow that fall during the winter. So there may be places in the Atacama, somewhere over here, where you get 1 millimeter of moisture every century, but it's certainly not up in the middle of the Atacama Desert where we thought it would be. So this has been a problem, not necessarily for observations, because it still is very dry. A typical observing session has 0.1 millimeter of water vapor from the top of the antenna all the way to space. So 100 kilometers up, there's just 0.1 millimeter of water vapor. So it's a fabulously dry atmosphere. And I'll show you why that's important. So here it is up here. Here's Santiago. Santiago's more or less halfway up Chile. If you have that pictured on the west coast of South America, Santiago's here. And an hour and a half, about 1,200 kilometers, is ALMA. It's about 2.5 hours away from the airport at Calama here. And there are two sites at ALMA. The operations site, which is at about 10,000 feet, and then the antennas, which are up at the high plateau at 16,000 feet. Humans can work at high altitude, but for no longer than 8 hours a day, and they can't overnight. Humans can't overnight above 10,000 feet, and so even our optical observatories in Hawaii that are 15,000 feet or so, you can't overnight above 10,000 feet. It's not safe. People certainly have lived at that altitude, you know, worldwide, but no one has really worked for extended periods. And so there are a number of university groups that are looking at the physiological effects of working at 17,000, almost 17,000 feet. It's really quite amazing. Okay, so 66 12-meter antennas, or 54 12-meter antennas, and there's 12 7-meter antennas with the spacing of 150 to 16 kilometers. And in the wavelength, in the millimeter wavelength range, using 10 receivers. We'll talk about that in a second. High and dry up here. Highest construction project, what is being built. Highest observatory, most complex. And it has the most proposals of any scientific instrument ever built. A cycle ago, we had just under 1,900 proposals. And these are peer-reviewed proposals by scientists. And the reason they're doing this, the reason that it's so popular, not only because it's a new instrument, but the submillimeter and the millimeter portion of the electromagnetic spectrum has really been underobserved. There have been small niche university groups here and there that have worked in the submillimeter for the last 50 years, but you need really, really dry areas, and there aren't that many dry areas on Earth that can support that. And so this is a frequency range that has been underobserved until ALMA came around. And as you'll see, if you'll agree, there's ALMA's making fantastic discoveries, and we're seeing the results that the scientific community is just ecstatic about this. It's a joint international facility. North America, the lead partner in North America is the National Science Foundation. We work with our colleagues in Canada and Taiwan. I know that Taiwan isn't in North America, but for historical reasons, we have partners from Taiwan. And we support operations and maintenance at 37.5%. Our partners in Europe, the European Southern Observatory, who also operate optical telescopes in Chile, support at 37.5%. And then East Asia, which is primarily Japan, but also Taiwan. Taiwan is in there as well. They take the balance of 25% of funding. And then, of course, the facility, the land, is provided by the Chileans, who automatically get 10% of the observing time for their contribution of the land. There are the two facilities that I mentioned, the observatory support facility that deals with operations and housing, and the array operations site, the so-called high site, where the correlator is and the antennas are. But this shows you atmospheric absorption down in the millimeter part of the spectrum. And there's significant absorption, where it goes down to 0, of course, and the bars show the receivers that operate in those frequency bands. And they're designed around the atmospheric absorption, of course. This is atmospheric absorption at ALMA, so this is in a very, very high dry site. If we were down here at sea level, this is almost completely blocked out. Yeah, because the supercomputer needs oxygen, and so the correlator building is oxygenated, but even at that level, it still is derated from if it were at sea level. Here's the high side, here's the correlator building with the antennas. Notice these pads. Each antenna can be moved around to change the baseline, and they are over the course of an observing cycle. And that's no easy feat, because number one, they're about 100 tons each. And the receivers that are used for ALMA, because we're observing in the millimeter, the astronomical sources that are emitting millimeter wave radiation are very cold. They're only 2 to 3 to 4 degrees above absolute zero. Cold gas, cold dust, we'll be talking about that shortly. Because of that, the receivers need to be cooled to that temperature as well. In fact, they are cooled to 3 degrees above absolute zero with liquid helium. They don't all have those hydrogen masers, but there are about 10 of them spread throughout the system. But because the receivers are under cryo conditions, they need to be maintained that way with continuous power. And so when the antennas are moved around, and I'll show you the transporter, which itself is an amazing device, they're lifted off their pad and they're moved around. They need to be plugged into power so that the receiver package, cartridge as it's called, never loses power. Because if it loses power, it heats up by ½ degree in 15 minutes. And if it heats up by ½ degree, which it does in 15 minutes, it takes 2.5 days to cool it back down to ½ degree. So you don't want to do that. Okay, international consortia are great, right? Especially where the funding comes in. But one of the problems is that each international organization wants their heavy industries to be able to participate. And so there are there's 3 different antenna designs. There's the small antenna which forms a core, and I'll show you that, which is fine. It has its own design, and that's built by East Asia, Mitsubishi Heavy Industries, in fact. But the 12-meter antennas, there are 3 different designs. One for North America, made by Vertex in Texas, the Europeans, I don't know who the European construction is, and the East Asians, again, Mitsubishi. So you can tell the difference when you see an image of ALMA from now on. You know, I want to be proud of you, and so you can look at that and say, hey, that's an East Asian antenna. And the way you know that is the North American and the East Asian secondary support are curved. See, the East Asians, the supports don't go all the way to the edge of the dish, but the North Americans do. The European has the triangular shaped secondary support, and it has very smooth lines. The chief scientist told me that you know that they're European because they're sexy. These are the most precisely figured radio antennas ever constructed. So this is a panorama of when I was there. There's me with my oxygen. That blue is the way the sky really looks. It's quite amazing. And you get kind of the scale of the antennas. Okay, so here's a receiver cartridge. These receivers are made primarily by the National Radio Astronomy Observatory down in Charlottesville, the operating facility for the North American part, in their Central Development Laboratory. If you're interested, you should look them up online, nrao.edu. They are magicians. Now, they're not the only ones who are doing this for ALMA, but about 70% of the receivers are built by NRAO. The Netherlands has a group that makes them, Rutherford Appleton Laboratory. Taiwan is making some receivers for us. So it's other places as well, but NRAO is the primary manufacturer. And this is about as high-tech as you can possibly get, certainly in radio frequency work, but probably just in general. So this is a cartridge with one receiver, and from here, it's about a meter and a half tall. From here to the top is under cryogenic control. This is room temperature. This is a 100-degree Kelvin stage. This is 50-degree Kelvin, and then this is the 2 to 4-degree Kelvin stage. In a closed-loop liquid helium system, the cryo lab at ALMA, in the middle of the Atacama Desert, is the most complex cryo lab in the southern hemisphere. And the cryo engineer is a local Chilean who is among the best of the best. So this is a receiver cartridge. This thing now is about 1.5 meters in diameter, and this is what is inside of the ALMA. There are 10 slots. At the moment, there are only 8 receivers. One is under construction in Taiwan, and then the 10th one may or may not be built. But each one of these is those little colored bars that you saw on the frequency band, right? They are receivers for different frequency regions, and they require. So this is all cryo-cooled when it's sealed, and you can see they have different architectures because the photons behave differently. So here's a feed horn for one, here's a little mirror for another one, here's a different kind of feed horn for a third one. So each one is different because the physics of the photons coming in each of those wavebands is different. So the later, which I told you is the fastest supercomputer on Earth, is actually 15-year-old technology. And if we were ever to swap this out, all of this would be reduced down to one rack with current technology that's 15 years younger. Here it is again. Just kind of cool, sci-fi type thing.
Yes.
Okay, these guys are spectacular. These are the transporters. There's 2 of them. They're called Otto and Lore. They were produced by a German company, Scheuerle, who gave them to ALMA for free because Mr. Scheuerle just wanted his name on a cool thing that was purpose-built for this. They are unbelievable. So for 28, 28 wheel segments, that the wheels are about this big, and each one moves independently. Again, they pick up the antenna and then pull it up along this incline so that they can move off. The wheels turn independently. They can place the antenna within a centimeter positional accuracy. They plug in the power, And let me go back if I can. The cabin is here, but they can also be controlled remotely. And 2 big diesel engines that produce 1,700 horsepower of power. Half of that, more or less, to run the antenna. When they're at altitude, they're derated by 60% because of the altitude. So that's another amazing thing. They go about 5 miles an hour. They're moved from the assembly site, and for kind of biannual maintenance, they bring them down. But most of the time they're up at altitude. One other interesting thing is that the telescope can't tolerate vibrations as they're moving around. So this structure here is designed such that there's absolutely no vibration from the road from here above. I don't know how they did that, but it's hydraulics, I guess. Now, the problem here is that people aren't used to working at 17,000 feet. So there's all sorts of maintenance issues. The hydraulic lines and things go bad, and it's very dry in the altitude, and so lots of maintenance on these things alone. This is real time. They can slew that fast. Absolutely no noise. The only noise you hear up here are the cryo pumps, which make little chirping sounds. Kind of neat. Now they don't move them often like that, but that's not a sped up image. So it's really quite amazing. So the technology is fantastic, which is why don't normally talk about our telescopes that much, but the technology is pretty amazing. And so what is it giving us? Well, it's giving us this. So let's start up as far as we can go. These are well, it's all relatively new. These are the latest observations. So this is oxygen 3 at redshift of 9.1, which is about 13.1 billion light years away. And here you see the spectrum and then the image. And this is very, very interesting because, heavy elements, of course, come from the centers of massive stars. And you need to have multiple generations of massive stars to build up enough of these heavier elements and then spew them off into interstellar medium and built into the next generation of stars. And yet here we are 300 million years after the Big Bang, and we have significant quantities of oxygen 3. So this is a challenge. How is this happening so quickly? Early stars, shortly after the Big Bang, the first generation of stars only have hydrogen and helium to work with. And so models show that those stars could be much, much bigger than the stars that exist in the universe today. And maybe that's why you're just getting more of them, more material being generated in nucleosynthesis, and lots of these stars that are lasting just a very short amount of time and seeding the universe with heavy elements. But this is unequivocal oxygen 3 at 9.1, and so this is a remarkable observation from ALMA. Not quite as far, but this is 12.5 billion light years away. We're seeing the seeds of galaxies coming together and galaxy clusters. So this object here, when we look closely with ALMA, we see these little proto-galaxy fragments that will come together to form galaxies, and then multiple galaxies, and then you'll have a galaxy cluster eventually as time goes by. Here's another one a little bit further out, and each of these major blobs, but also these over here, those are all galaxies that are interacting with each other. And these streamers between them are physical linkages of gas flowing between the galaxies as they're forming. Of course, you're all familiar with the DHT result, right? Yeah. Did you know that ALMA was instrumental, no pun intended, in creating this image? Because without ALMA, it would have looked like this. And why? Because ALMA has a huge amount of collecting area, and it allowed us to get the sensitivity that we required here. And here's a 15 microarc second. Of course, this is the Event Horizon Telescope, so from the South Pole up to Greenland, and Greenland wasn't on the line. But still, 6,000 kilometer baseline gives you these phenomenally fine resolution elements. But without ALMA, this is what it would look like. And to be fair, there's a smaller submillimeter radio telescope on the plateau called APEX. and apex was involved in this as well, but the difference isn't much if you pulled apex out. Okay, then nearby galaxies. This is a survey of carbon monoxide, of the carbon monoxide molecule in nearby galaxies. And these are spiral galaxies, and they look like spiral galaxies in the visible. It's just that this is all carbon monoxide gas in star-forming regions. And so, we see the spiral arms because that's where the stars are forming, the bright O and B stars, and this is just showing that that gas is tracing the same thing. And then, if we have a galaxy, so here's the galaxy underlined from Hubble, and we overlay the carbon monoxide and various other molecules here in different colors. So that, it traces the star formation just as you would expect. And these are cold molecules, and you require those cold molecules to form stars. So that's exactly why we're using this these molecular tracers to find star formation. And at whatever angular resolution we're looking at, we see that gas in the universe forms preferentially into filaments and streamers. This is in the Orion molecular cloud, nearby a star-forming region that you can see tonight. Not like this. This is 290 astronomical units across here. But the point to notice here is look how the gas is formed as streamers. And if you remember the cluster of galaxies that was forming, there's a streamer of gas at a bigger scale. But kind of at all scales that you look at, gas is forming in these streamers. And it's just the way the laws of physics seem to work with gas and fluids. ALMA has done tremendous work in star formation and protoplanetary formation. So here is a disk. There's a protostar, a newly forming star in the middle here that we can't see. It's surrounded by a disk of dust and molecules. And the dust, by the way, that ALMA detects is like pea gravel type of size. So 5 to 10 millimeters to half a centimeter or so. And then jets, nature likes jets. Jets are around supermassive black holes and in newly forming stars. The star is forming with a dust cloud around it. There's magnetic fields that filter up through that dust cloud. As the star rotates, as the cloud rotates, the magnetic field gets braided along the top and bottom spin axis, and then charged particles get shunted, north and south in essence. And so that's what this jet is. But if you notice, along the left, there's kind of the pinky purple, and on the right, there's blue. So that's Doppler imaging from ALMA. The red is a redshift, that is, the rotation is going into the board, and the blue is the rotation is coming out. So with ALMA, you get this Doppler, you can get the Doppler rotation effect. Before ALMA, these are millimeter wave observations of protoplanetary disks around stars, newly formed stars. And these are contours of the light levels overlaid on an image here. Here's a scale of 100 astronomical units, so if our solar system were there, it would be way out in the Kuiper belt and beyond. And so this is the previous state of the art. So take a look at this guy and this guy here, because that's what they look like now with ALMA. HL Tau on the left, this was the engineering image from ALMA. This was the first image ALMA made. The current deputy director was a postdoc working with, this was his expertise, and he was in Santiago shopping Saturday morning when they texted him this image. He had to stop because he broke down crying while he was So what we're seeing here are gaps in the disk of the protoplanetary disk, gaps that are caused by orbiting planets, cleaning out the dust and debris that's in that disk. Now, I will add that that's the currently most accepted model. There is another model that says the planets, in fact, are in the bright regions, in the bright rings, and they set up gravity waves, and the gravity waves clean out these regions here. That's about the 25% accepted model. It goes back and forth between the two, but at the moment, it's starting to coalesce there, that the gaps are almost certainly where the planets are forming. And here's another one almost edge on. And when we look at newly formed stars, they have debris disks around them, and they all have these sort of things everywhere. Look at, here's a double star system, and with both of them with disks that are canted. Here's another double star system that only one appears to have a planetary disk around. But all sorts of things all over the place. Now, you know, other observatories are detecting exoplanets, but older exoplanets. These are exoplanets that are in the stage of formation. This is even more amazing. So those were protoplanetary disks, right? Those gaps are where planets are forming. Here's a protostar in the middle here with a disk around it. And it has these little overdensities, which are apparently planets. Now, this isn't, you know, there's a little blob there. That's not a planet. That's a blob of gas and dust because it's relatively large. But notice the one on the right. There's something around it. And the interpretation of this is that that's a circumplanetary disk where moons are forming. So maybe like a Jupiter-type planet with the moons forming around it. This is the first time that that's ever been observed. And so this is ALMA. This is ALMA with other ground-based observation, and you see the same thing. So over here you can say, well, this is just an instrumental effect. But when you add the other data from an independent telescope, it's clearly, here's that big blob, that's the planet, and there's the thing over here. So that's clearly a disk of material around a forming planet. That's pretty spectacular. What these are showing is the Snowline. So where you are freezing out the molecule onto a dust grain in the outer regions of that planetary system, and then in the interior region you have carbon monoxide as a gas. It's not frozen out. So the Snowline here occurs at this point at like 50 astronomical units, so way out in the distant part, and then you have not liquid, but your temperatures are warmer, of course, in the middle. Now we're back into our region of the universe and the solar system. So ALMA does solar system observations as well. And you see the nice ring of Uranus. Here's Jupiter from last year, observation from last year. The bright bands correspond to the dark bands in the optimum. So this is upwelling gas coming from the interior, coming up, and it's hotter than the surrounding areas. Europa, ALMA has been working with NASA to define the Europa mission through observations. This is a spectrum in the frequency range you see here, band 10, and each of these lines is from a molecule. The vast majority of which we have no idea which molecule it is. Partly because the laboratory work hasn't been done. Molecules are very complex, and their spectra are very complex, right? Molecules, even if you have a 2-atom molecule, what's producing these photons is rotation of the molecule, vibration, and bending, and that sort of thing. So that adds to the complexity. Laboratory work hasn't been done to the extent that we can identify all of these. So a couple of them are here, and here's a carbon isotope with carbon monoxide. Underneath here shows you the Herschel Space Telescope that was optimized for this work, and it's just turned upside down so you can see it a little bit better, but you can see how much better ALMA is. And so lots of work for the laboratory astrophysicists, but also lots of work for understanding molecules in the cold molecules in the universe. So of course, DHT Results, you all know and love that, right? This is part of the EHT team looking at the 7 different newspapers that had it on headlines. Up until this, in April of last year, the single most viewed, whatever the terminology they use, interacted with event on Earth was the Mexico winning the World Cup. And it had between 3.9 and 4 billion interactions. And the ALMA event in April, as far as we can tell, it had between 3.8 and 4.2 billion. So we're either the top event that's ever been observed, ever been interacted with on Earth, or we're the second to the Mexico winning the World Cup. But nonetheless, that's a pretty spectacular thing for any scientific result, certainly an astronomical event. M87, the giant elliptical galaxy, and we're looking really at just kind of the central region, and then off to the left here is the bright active nucleus, the supermassive black hole that we knew was there because this jet is here. The jet is about 5,000 light years long. It's made up of electrons and protons, moving at about 97% the speed of light. The jet is launched in a way that we don't yet understand. That's current ongoing research. What's the black hole doing? Where does the jet come from? How is it, how is it produced? But what we do know is that blobs of material, blobs of charged particles, are emitted from the region around the black hole. And there's little twists and things, and the black hole certainly is precessing as it, not only is it rotating and spinning very rapidly, but it's also precessing, which is probably why you're getting this sort of structure. But okay, why are we looking at M87 with DHT? Because black holes are very small, and our technology is advanced, but not advanced enough to be able to see them in many cases. In fact, there are only two objects that that a telescope the size of the Earth can observe, and that is the supermassive black hole in the middle of our galaxy and M87. And M87, because even though it's far away, 55 million light years or so, it's a big, big, massive supermassive black hole. We knew it was big. With the EHT results, we now know it's about 6.5 billion times the mass of the sun. So this is a model from the EHT team of the region around the black hole. And this isn't the accretion disk that you're seeing. There's an accretion disk out here, but these are photons from the accretion disk that are being bent around, primarily around the black hole. So most of the light from over here is coming from the backside of the black hole, and as it's moving away from the black hole, the gravity of the black hole is causing it to bend back and come to our line of sight. Now that stuff is rotating, so that's why you're getting the rotation here. So, and of course you guys are a savvy audience. We're saying we're looking at the black hole, but of course, by definition, we can't see the black hole, so we're looking at a shadow of the black hole on its surrounding environment. So here's the image that you've all seen with our solar system superimposed in there out to Pluto. I don't know if you've seen that before, but that's kind of a neat. So, you say supermassive black holes are solar system scale, and that's what they are, with 6.5 billion times the mass of the sun in that region. Just remarkable. And there it is without that, so you can see what it looks like. So, pretty amazing. Oops. Okay, so that unified model I showed you, it had the black hole in the middle, it has the accretion disk, it has the jets, and then it has this thing that's called a warm Ion Torus. And we always expected it to be there because you can see evidence of it when you're looking at various angles. You can see it eclipse stuff from the accretion disk. You can see it kind of see it indirectly glowing. You can see it glowing kind of indirectly, but you can also see reflected material like this image shows, stuff from the accretion disk reflecting off and then bouncing back in our direction. But we've never seen it directly until last year when the Very Large Array observed Cygnus A, a giant elliptical galaxy 760 million light years away. And here we see it in the radio with the radio jets oriented more or less like this. And there's some hot spots which appear to be where the jets are launched. And then there's this emission here, which is coming from this torus. So this is the first ever direct image of that warm, dusty torus around the accretion disk. Yeah. And then to note here is this bright object, very bright object in the radio that was discovered for the first time in a survey in 2016, and it's still there. This appears to be a second supermassive black hole. And of course, LIGO, right? The Laser Interferometer Gravitational Wave Observatory, Interferometer Gravitational Wave Observatory, that detected gravitational waves for the first time in 2015. Those gravitational waves came from coalescing black holes. So this is the discovery image of the two observatories and then combined. Of course, I'm sure you've heard the sound. There it is. It's the travel time. By the way, you hear that, now that's sonic. The signal doesn't come in that way. It's been created so we can hear it. These are photons, but you hear the pitch increasing. That's as the black holes are coalescing, and then that little chirp at the end is the ringing over here after they've gone together and it's kind of wobbling. So here's the amazing thing that we've discovered from LIGO in relation to black holes. This is a depiction of the progenitor black holes and then formed the more massive one as they collided, coalesced. And so here's the amazing thing is that these black holes presumably are coming from supernovae, exploding massive stars. And when you blow up massive stars, our models indicate you can create a black hole that has a size of 3, 5, 10, maybe 20 times the mass of the sun. But yet we're observing black holes before they collide, right, of 30 and 40 and 35 and even more. This is kind of dated. We've seen them up to 60 times the mass of the sun. We have no idea how those black holes have formed. So this is a big unknown. Where do these big stellar-sized black holes come from? Black holes are apparently in the centers of all galaxies, spiral galaxies, elliptical galaxies. But now we're starting to find them in the outskirts of dwarf galaxies. Dwarf galaxies are kind of, amorphous things that don't have structure. They're typically very small, 100,000 to, 100 million stars. No set structure, and yet we're seeing supermassive black holes in them, and not in their centers, but in the outskirts. And these aren't, now they're not big supermassive black holes, but they're 3, 4, 5 million, 10 million times the mass of the sun. So the picture that's being painted here is that these big black holes are forming in some way in the outskirts of these dwarf galaxies. And then probably in the early universe, all these dwarf galaxies are combining to form bigger galaxies, and the black holes that are in their outskirts are now falling into the middle of the resultant big galaxy, where they coalesce and form supermassive black holes. So this is really quite intriguing. Again, these are all completely unexpected observations that are just coming out. And then, as with that first image from ALMA, we have an observation of a supermassive black hole. This is an artist's depiction, of course. Supermassive black hole that is really large, 800 million solar masses at 13 billion light years away, only just under 700 million years after the Big Bang. So not only are we forming stars and heavy elements very early on, we're forming big monster black holes in a way that up until now we didn't think there was enough time to form big monster black holes this large. The Big Bang doesn't create big black holes like this, as far as we can tell. So where are these guys coming from? That's so this is one observation. There's been another 2 now of very large supermassive black holes very, very early in the universe. So a lot of neat things happening. That's what astronomy is all about, right? We're still in discovery space where not only are we making new observations that are challenging current models, but we have new instruments that are making new observations that are telling us new things.